Hope you're all doing well. Just to ease kind of this transition into remote teaching, what I wanted to do is just to go over a quick review of Lecture 6, so nucleation, growth, and oswald ripening, what we covered before our extended hiatus when my conference was canceled, and then, of course, our 2-week spring break. So I just wanted to go over kind of some of the key aspects, the key fundamental and physical understanding. One thing about Lecture 6 is that there's lots of derivations. Don't get too caught up. Obviously, go through the derivations. It's really helpful to kind of really get a true understanding of what's happening, but don't spend too much time on the derivations. Understand kind of the real critical and key physical aspects of what the equations are telling you, and hopefully that'll help after we kind of do another review today. So in this video, we're just going to go through kind of curvature and how that leads to this kind of chemical potential driving force for 2D grains to either grow or shrink. And then the next video, we'll move on to kind of oswald ripening, since that's our kind of our 3D case. So just to give some motivation as to, again, why are we even talking about this? So from our Lecture 5 phase diagrams, and again, all of this is in the OER. I'll post it in the link to this video, but of course I would stick with our lecture notes and our presentation to get the kind of full understanding of what's happening here. So just to kind of give a background, so in our, let me get my pen up here. In our phase diagram lecture, we saw and we know that there are some scenarios where you'll get basically some mixture of liquid and solid. So I have some solid, some liquid, and over time, we know from our phase diagram at certain temperatures and certain compositions what the fraction of those liquid and solid, so these are, let me write here, solid, 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 again, usual, red is our solid, blue is our liquid, so liquid is everywhere else around here. So we know from our phase diagram what temperatures and what compositions will get this mixture, this kind of two-phase region of solid and liquid, and what fractions of each will have. However, we don't know from, again, just from purely thermodynamics, how will this solid particle, how will it change, the size change in time? Will it increase? Will it decrease? What's the rate? And that is not given to us by thermodynamics. That's given to us in kinetics. So this is, again, a kinetics lecture, just like in lecture kind of 4, where we're talking about kinetics. So this is kind of going back and kind of finishing up kinetics in material science. So I'm just going to erase this real quick, just to give me some more room. So we have talked about previously, and we talked about last time, or previously in class, we had to kind of introduce, whenever you're creating kind of this solid and liquid kind of 2D, or not 2D, excuse me, two-phase region, you're creating basically surfaces. So I want to highlight that here. So creating new surfaces, whenever we do that, this is our, again, our fundamental Gibbs free energy. And we know that we want delta G or dG to decrease. We always want Gibbs free energy to be negative. That is favorable. If delta G or dG increases, if it's positive, that is not favorable energetically. So creating new surfaces, that increases your delta G. So this is not favorable. Creating new surfaces is not favorable. We have to pay an energy penalty. So dG or delta G increases. So that is not good. So this is going to come up a lot in this lecture. So whenever you're creating new surfaces, you're paying an energy penalty, you're increasing Gibbs free energy. We always want to decrease Gibbs free energy. That's kind of these spontaneous reactions. We always thermodynamically want to decrease Gibbs free energy. But when you create new surfaces, you create basically this interface between, and we'll see here, solid on one side, liquid on the other side. It could also be like component A on one side, component B on the other side. Whenever you have this interface here that separates two unlike materials, we pay that energy penalty. So again, that's just the basics of kind of what we're talking about here. So again, sorry for, I'm going to have to erase. Let me erase this. And bear with me. Unfortunately, this is not as nice as the whiteboard where I could just kind of move around. But we'll adjust to this. So let's look at the equation. If we're creating new surfaces, we have to introduce this new term, which is our surface tension or surface energy term here. So gamma, if you remember, is in units of joules per meter squared or Newton meter. So this term, it's either called surface tension, surface energy. You'll kind of see that interchangeably in the literature. And again, you could kind of see it written in terms of the partials here, but this is going to count for creating these new surfaces. So that's what kind of comes into play there. So we have to introduce this free energy term. However, we talked about last time, you see that it's a little bit unfortunate because, again, we always have our chemical potential term here, and now we have this dN and dA. So the one key distinction here is, remember, this mu subscript P is not our traditional chemical potential right here that we've talked about before in lecture 5. So here, chemical potential we've defined previously as the partial derivative of Gibbs with respect to the number of atoms at a constant, so that's what this means here, constant temperature and pressure. But we are now working with assuming that basically constant temperature, pressure, and area here. So that's what's the difference here. Remember, we kind of called this the chemical potential of an infinite plate. So again, this is just background, but that's what we kind of built up last time in class. So now the question is, how can we write, really, there's no scenario where A is constant. Because when you change the number of atoms, A can really never be constant. As you change the number of atoms, you're changing the area. So we went through in class, and in the notes, you can kind of read through this here. I'm going to skip and change now. Excuse me. We went through this whole derivation for the relationship between dA and dN for the simple case of a sphere. So let's take a stopping point right here. We talked about this in class. We talk about spheres a lot when we talk about basically creating new surfaces or precipitating particles. And you'll see in material science, a lot of times, you'll see precipitates or particles or solid particles that nucleate from a liquid. They will typically have this spherical shape. So they'll be a sphere. Now, what is the reason, or why do you think that could be? Well, we just said that to create surfaces, that's energetically unfavorable. So creating surfaces is bad. We have to pay the energy penalty. So, because associated with a surface is that boundary, right? So associated with a surface is some surface area. What's unique about a sphere compared to every other kind of geometric shape? Well, a sphere has the largest volume to surface area ratio. So that is your volume to surface area ratio. It is the largest for a sphere. That is the geometry. A sphere has the largest volume to surface area ratio. So that's great, right? Because again, Gibbs free energy, delta G, we're always trying to decrease this. We said that creating surfaces, so creating surface area is horrible. So we want this to be as small as possible. We want this ratio overall to be large, right? We want to shrink this. We want to increase our volume. That is going to decrease our Gibbs free energy. So a sphere is perfect for, again, trying to achieve this because it's minimizing the energy penalty we have to pay. So again, just like we talked about in class, that brings up the scenario. If this has the largest volume to surface area ratio, Amazon, especially in nowadays, why don't they just ship in spheres instead of boxes? But again, take that idea, run with it, start a new company. But we're going to use this concept for nucleation and growth instead. So in the notes, we went through and did this derivation to see how we could rewrite and connect basically dA and dN. Sorry for that tangent, but it was important for understanding. And you can go through these notes. Again, this is just kind of math at this point. But we introduced and we got this key expression right here. And this is what I want you to focus on. The chemical potential for a sphere at constant temperature and pressure, remember, because now there was this whole derivation, was getting rid of the dA. So we wanted to eliminate the dA term right there and rewrite it in terms of dN. So now we have this equation for the chemical potential of a sphere is this, and really it's going to be, as we're going to see in a second, actually I'm going to write it down right here. So chemical potential of a sphere is really plus or minus this term, and we're going to see that in a second. And we're going to rewrite this term, there's a special name for it, curvature. We'll come back to this in a second. So really, this value here can change. It can be either plus or minus, and we're going to see that in just a minute. So why is this important? Why is this such a critical, why am I highlighting this? Why am I saying you need to kind of know equation 12 and keep that in mind? That's one of the key highlights of this lecture. Well, because it is going to tell us a lot about which particles or which interfaces are going to move and how they're going to move and what directions and where atoms are going to flow. So curvature is really, really, really critical here in this lecture. So we said in general, so when you have this curved interface, so if I'm separating, material 1, material 2, remember this could be either like a solid or liquid. Again, this is just a general case. But if I have this interface, separating these two materials, or 1 and 2, whatever you want, the general expression for curvature is this. So if you have this ellipse shape, you're going to have, so this principal radii like R1, sorry for that, and then this principal radii R2. So what is going to be the curvature for a sphere? Well, R1 is equal to R2, which is equal to R. So my curvature here is just going to be 2 over R, right? Now, the key aspect, and what you'll kind of see down here, is how do we define if the curvature is positive? How do you find if the curvature, is it positive or negative? That's going to be kind of the key aspect that we're going to kind of think about. So it all depends on, basically, again, what's another way we can kind of think about or talk about curvature? Well, or mathematically. So if I have a function, y of x, how can I tell, some function here, excuse me, I'm going to erase that and draw it a little bit nicer, even though I'm talking about it. So let's do, if I have a function y of x, how do I tell if this has a positive or negative curvature? So hopefully, you remember back from mathematics, if I take the second derivative, and actually from lecture 5 as well, when we talked about stability, if I take the derivative of y with respect to the second derivative, if this is greater than 0, I have positive curvature. If this is less than 0, same derivative, part second derivative, set it equals 0, second derivative, if it's less than 0, it is going to have negative curvature. So, if I'm sitting at this, if I'm sitting at 2, is my curvature positive or negative? If I take the second derivative of this, is this positive here or is this negative? Well, it's positive. So this 2 has positive curvature. 1, if I'm looking over here, and again, you can think of it as an unstable point, right? I'm at the top of this hill. If there's any little fluctuation, I can roll down this way or this way. But again, if I'm sitting from right here at location 1, 1 has negative curvature. And you can just tell that from, again, that second derivative of the equation. So you can see here the curvature sitting at 1 is minus 2 over R. The curvature sitting at 2 is positive 2 over R. So again, that is I can't explain or kind of emphasize enough how powerful that is. And we'll see why that is in a second. Because if you remember back, we had this expression for chemical potential as a sphere was this infinite plate plus or minus 2 times your surface tension times this over R. Notice here, we have basically curvature right here. So we could write this expression, or rewrite, excuse me, I'm just going to erase like that. The chemical potential for a sphere is going to be chemical potential of a plate plus or minus curvature, kappa, d bar. So our chemical potential will change depending solely on this parameter here of curvature. Because really, this surface tension, this is not going to change. It will change if you change your materials. So this is basically a constant for a material. It will change if you change your material. So like if you're melting a vat of copper, so you took copper and you're melting it, and then you're trying to precipitate in solid copper, right? This will change if you change from copper to iron. Same thing with V bar. V bar is your molar volume. Again, it's shown in the notes. That will change depending on your material. But once you've selected a material, really the only thing that's going to change in this expression is your curvature. That's the only thing that's going to change kind of the parameters here. So this will control your chemical potential. We'll see why that's important in just a second here. So let's go back. So now, again, this is just rewriting out the chemical potential at 1 and 2. The key kind of parameter here is now you have this chemical potential, this driving force that is going to drive essentially diffusion. So if you remember back in lecture 4, we had Fick's first law, which was grad C. If this is 2D, we had dc dx. One of the things, again, we mentioned, again, assuming that we're in 1D, grad C is very closely related, and we showed this, again, read the OER in lecture 4 just to kind of refresh. This is very similar to a gradient in chemical potential. Gradients in concentrations and gradients in chemical potential are pretty closely linked. Again, there's some factors here, but it's approximate. So we know from first law that if you have a concentration, if I have a little of that, and if I put my like invisible wall here, and I have lots of kind of high concentration here and nothing there, if I release and remove this wall, or if I wait in time, I know that eventually we're going to flow from high concentration, again, just due to Fick's first law here, I'm going to go from high C to low C. We're going to evenly distribute. There's going to be a flux of atoms going this way. So if C and a chemical potential are very closely linked, there's going to be some driving force that's going to drive diffusion in this scenario here. So let's go back and think about, I'm going to go back up a page. So let's think about where will atoms flow here. So where is chemical potential high? So like we just said, this is a constant, this is a constant, this is positive, this is positive. This will be positive as well. Sorry for all the writing. So if my curvature is negative, is that, which is the case over here, right? So here curvature is negative. So is my chemical potential, which is higher? Chemical potential of 1 or chemical potential of 2? Chemical potential of 1 is less, or chemical potential of 2 is greater than chemical potential of 1, right? Because chemical potential 2 is positive, this is negative. It's going to decrease this value here. So we have, let me kind of do a little bit of erasing here. This isn't important anymore. Got this. So here, I've got high chemical potential, so high mu. Here I have low mu. So where are atoms going to flow? Again, same thing, right? Fick's first law, D, you could even think of it as grad chemical potential. We're going to flow from high to low. So atoms are going to flow across here. They are going to move from 2 to 1. That's kind of a key aspect here. So atoms are going to flow out that way. We're pushing and moving towards there. So remember back in lecture 4, the Kirkendall effect. Whenever you have atoms flowing here, they're leaving here. Now the atoms are kind of pushing on this interface. The interface is going to move. Your curvature or your boundary is going to change. And it changes. So remember, this was our initial interface right here. So this was what I was drawing before. So as atoms flow from 2 to 1, they're going to pile up here. Your interface is going to move from here to here. Your interface is going to move this, again, from 1, here we go. Oh, sorry, excuse me. Here to here. It is going to move some distance, delta x, based on that change in chemical potential. This driving force right here. So as those atoms flow, the interface is going to move, and it's going to shrink. Basically, 2 is going to shrink. So grain 2 will shrink. Grain 1 will grow, based purely, again, on this difference, this driving force in chemical potential. Just like we saw the Kirkendall effect, it's all it is just driven due to curvature. So this is an amazing finding. Again, purely from curvature, we can figure out which grains are going to grow and shrink depending on where you're at. So that's a kind of a key, the fundamental finding here. And it's just from that simple expression of the chemical potential that is just driven by curvature. So you can get a little bit fancier now. And again, read through the notes and see, we can then relate this change in chemical potential to this driving force here. So this delta G will have this kind of work term. So I hope you remember. So work, I think probably in physics 53. So work is just going to be some force times distance, delta x, and that's going to give you units of, again, energy, right? Because This is Newton. This will be a meter. Newton meter is equal to a joule. So just kind of a reminder there again, a nice expression to have. You'll see this pop up over and over and over and over and over again wherever you go. Even if you're not a material science, if you're civil engineer. But the key expression you can kind of get from this idea of converting it into work is this equation for stress. So here, this is a really powerful, again, we're going to talk more about stress. We haven't got to that yet. We're going to talk about that in lecture 7. But stress is basically, just a quick preview, is force per unit area. It's actually much more complicated, but we'll talk about that more in lecture 7. Force per unit area, you can see here, the stress is, again, so stress is this expression here, 2 gamma GB of your grain boundary or whatever it is times kappa. So this is just a constant. So that will not change. This will not change, again, depending on your material. So you can see that stress is directly proportional to your curvature, which is either going to be plus or minus 2 over r. So you can see that as your curvature, as your radius of curvature shrinks, this stress is going to blow up. It is going to increase dramatically. And why is that again? It's the same idea. It's the same idea, again, coming back, our expression for the chemical potential of a sphere is dictated, again, that's also directly proportional to this curvature, which is, again, 2 over r. So as your radius of curvature decreases, your chemical potential gets larger and larger and larger and larger. The driving force, delta mu, gets higher and higher and higher and higher. And the stress that's pulling, essentially, acting towards the center of your curvature will pull the boundary more and more and more and more. So there's this nice connection between, again, this whole driving force, stress, all based upon this key parameter here, curvature. So that's about it for this video. We're going to talk about kind of the kinetic aspect, another way you can kind of think about nucleation growth kinetically, and then we'll move on to, after that, 2D grain growth and then Oswald ripening. So I hope this has been helpful. Please, again, if you have any more questions, if you'd like to see more examples, let me know. And again, just please be safe, stay healthy, especially in these times. And if you have any questions, just please be sure to email me or ask, and I'd be happy to provide essentially more explanation or more examples. But yeah, have a great one.